Okay, this example is 2.1 in your textbook, and goes over the basics of finding both average and instantaneous velocities. So the situation given is that we have an observer and a vehicle. I traced out the same number line given in your textbook at x equals 0 meters. And they are watching a cheetah, which is 20 meters east of them, starting up and beginning to chase an antelope. And these are some of the given values on the number line in your book. So we're first asked to find the displacement between t equals 1 and t equals 2 seconds. The only thing we were given, other than some of the values on the number line, is our displacement as a function of time. Whoops, don't want that there. We're given the displacement as a function of time down here in the form of a formula. So what we need to do to answer question A is to simply plug and chug numbers through. Displacement is a value of where you started to where you ended. So we often give displacement, since we're on the x-axis, this is horizontal linear motion, we're looking for really what we call delta x. So to find delta x, we actually have to find x at time 2 seconds and x at time 1 second. Now your book denotes it as x2 and x1, so I'll use that notation. We also might see it shown like x2 minus x1 is another possibility, which you may see me write. Either one means the same thing. So all we have to simply do first is take x at 2 seconds and plug in 2 everywhere in the formula we see t. So we need to find these separate. So I'm going to leave the units out while I'm doing the calculations, just so you do the numbers. So we will have 20 plus 5.0 times 2 squared, 2 seconds squared. Running those numbers at t equals 2.0 seconds, this number comes out to be about 40 meters. And if we do a similar thing, we'll do it right here for where I am at t equals 1 second, because that's an unknown as well. We need to run a similar pattern here, 20 plus, I should put, 5.0 and then 1 squared. This gives us 25 meters. And then finally, I'm running out of room here, so I'm just going to do it in red right here. Delta x, which is just subtracting the 2, which we noted before, which represents the displacement, or from where I started. The difference from where I started and where I ended is simply going to be 40 meters minus 25 meters. And delta x is going to equal 15 meters. Alright, moving on then to part B, which says find the average velocity, which, well, we pretty much already have the setup. The general equation for average velocity is v, and we have the subscript Av for average. A dash x just means on the x-axis is change in x, so we just already found that, so we can start plugging into this. So we got 15 meters divided by the time interval, which is just the time interval we found that displacement with a moment ago. So that would be 2.0 seconds minus 1.0 seconds. And 15 essentially divided by 1 gives us an average velocity of 15 meters per second. Well, that should be pretty simple. Velocity is just delta x over delta t. More common way of saying it that's not quite as technical as your book uses is v equals d over t. But we're going to use, in most cases, follow the variables your textbook uses, which would be delta x over delta t, or if we're on the y-axis, it would be delta y over delta t. All right, moving along. So far, so good. Part C we're going to discuss in class. It's just kind of there to prove a little bit of the calculus involved in Part D. So rather, you could take a look at it yourselves if you'd like, and we'll discuss it in class. But the way you're typically going to do it, once you learn it in here or learn it in your calculus class, is like in Part D. So basically it says, the way it's worded in your textbook, it says derive a general expression for the instantaneous velocity as a function of time and find it at 1 second and at 2 seconds. So we're just going to simply go back to the given formula as a function of time for your display or your position, which would be 20. Again, I'm just going to leave out the units for right now just to do the math. So leaving out the units, which are important, but well, taking care of the math, I don't care if you have them there or not. This is the function of position and time. So if you haven't learned it already, it's simple power rule of calculus to take what we call the derivative of this. And just to remember what that really means, the derivative is basically taking the slope of a line at any given instant. We're trying to find the instantaneous velocity at 1 second and 2 seconds, not the average like we did in Part B. So this is a very simple derivative where once we take the first derivative of the position time equation, it will represent a velocity time equation. So the derivative of a constant is 0, so that number basically goes away. And using basic power rule, we take 2 times the 5.0 out here, so we'll have 10.0, and subtract 1 off of that exponent. Again, just following the power rule, and we'll get a velocity time function equivalent to 10.0 times t. So when I find v at 1 second, which also you might have it as a subscript of 1 down here, just get used to seeing me do it either way, I simply plug in 1. So at 1 second, it's just simply 10.0 times 1.0, and obviously that's still going to be 10.0 meters per second. And then again, simply if we want to know it's instantaneous at that moment velocity at 2 seconds, we could use the same equation, just plug 2 seconds in there. So we've got 10.0 times, a little squiggly there, times 2.0, which is obviously going to be 20.0 meters per second. So as long as you have a rough understanding of calculus at this point, it doesn't take much, but the reason why we cannot use this basic algebra here is because the velocity time graphs, if we would make them for this situation, would be curved, possibly. We'll talk more about that later. So what we pretty much have going on here is taking the slope at a given instant, which gives me a velocity. That'll make more sense once we talk about it more in class if it doesn't right now.